Let me define us to be back to business. Yeah, I just had a good question during the break. When I was doing the double copy at 3 points, I was multiplying two amplitudes and looking at symmetric or antisymmetric combinations of little group indices, computing what I get, and then I could just identify those amplitudes with the gravitational amplitudes that I get from here. So this was a match. It happened that they were nicely matching. For the symmetric combinations, it was almost obvious. Well, it is obvious in this notation. For the antisymmetric combination, you had to use that other set of properties, and it came out. So yeah, it was a match. It didn't have to be this way before we did the match. It's like how the double copies tend to work, that if you don't know, you know that double copy should give you some gravity theory, but identifying the gravity theory is one of the hard parts of your research. So what I was doing there was matching double copy amplitudes to gravitational amplitudes and seeing that there's some that I can do it, and therefore I know something about the double copy theory. So yes, for some theories which have a lot of symmetries, and these theories define them uniquely, you look at amplitudes, you know the symmetries you have. If those symmetries define a gravitational theory, that's the theory that you're looking at. But in this case, there's little that I know about the output theory of QCD times QCD. So whatever we were doing, that paper was really going order by order and trying to make statements about what we get. Yes.
I mean, in the spin a half and spin zero case, isn't it embedded in n equals 4 supergravity?
Yeah, probably.
Copy with supergravity?
Yeah.
Not a higher spin case than
Yes. That's right.
And also, I guess the KLT relations were originally derived from massless particles.
Yes.
Did you want to say something about why you can apply them to massive particles?
Yeah, well, first of all, it has been proven that at tree level, well, actually, I'm going to get to that, to similar statements very soon. So maybe I postpone that. Yeah. So yeah, I was in the middle of the derivation. I massaged my residue here to this form. So now the only thing that I need to compute is this bracket. So let me do it. Let me do it on some board space. So this was this momentum. Since everything is incoming B. Now I just open it up first. P1 plus P2 minus 2, 1, 2, 3, 1, 2. And the shifted momentum is 3 and 2. So that is in between 1 and 4. So getting to the same to the common denominator. I first of all act with P1 on 1. I get minus M 1A4. Still this factor that I multiplied by. On this side, P2 contains 2 bracket 2 angle and bracket 2 square. So I can just write 2 4b. So I unify this term and that term. So what I get is 1, 2 comes from here. Since I multiplied it by 3, 1, 2, I have to write it. And from this term, I get, with a minus, 1A, 3, 2, 1, 2. Close. Again, I see a Schouten identity with respect to spinors 1, 2, and 3. So what I get is 2, 3, 1A, 1, 2. So this is minus M 1A2. So I gain myself a factor of M explicitly in front. And so this term becomes 1, 2, then 2, 3, then 2, 4. And this term I rewrite with switching this momentum to 4, 2, 4, 3. Now I can do, I can see that there's a momentum 2 sitting in here, which by momentum conservation I can flip back to 1 and 4. Three, 2, 4. What happened? Do you still hear me? No, it's out. No, it's on. And here I can do another Schouten identity with respect to brackets 1, 4, and 2. I get 4, 2, 1A, 4, 3 with a minus, and 4, 2, and now 2, 1. 2, 1, 4, 4, 3. Now I see that this term cancels with this term inside this bracket. And the remaining part is here I get plus M 1A 3 times 2, 4. And here I get minus M 4B3. So with respect to this minus, it becomes a plus, and 2, 1. Great. Oh, now it fell. Great. So all in all, I've massaged my bracket into M squared 3, 1, 2. And this term looks nice like this. And that term is right. So plugging it back in here, I get well, I see that all the powers of mass cancel, the no explicit powers of mass, and I get, well, this thing 312 to the minus 2s. It sits downstairs, unfortunately. And 1a, 2, 3, 4. 2s. 2s. If you cannot see it. Has anyone copied? Everyone copied if they wanted to copy that? So I've just identified this residue to be that expression. As one of the exercises, it's the exercise. What is my? Well, the exercise number, whatever. You can compute the other pole, the residue of the other pole, and see that it is equal to the same thing, but with the S13 here and SDC here. So that's the exercise to compute it. But let me just write the complete amplitude now. So it became this. Oh, I forgot to. TCTD. So this is the one I computed explicitly. And that's the one you can compute in your free time. And the bracket in front is the same, 312, 2 minus 2s, 1a, 1, 2, 3, 4, plus 1, 3, 2, 4, 2s. And just in the same way, you can compute, whatever. You can compute the other amplitude, 1, 4, 2, 3 with pluses here, maybe C, D, I, J, and it becomes minus 1. It looks very similar. So now there's something to discuss right after I write it. Some interesting properties to inspect of these amplitudes. Can you still see it? Oh, it's not writing so well. 2, 3. no, there was no square. So the all plus amplitude contains an explicit power of mass in the denominator. So this is interesting. Well, so this is what happens for s bigger than 1. Yeah, I think it's hard to see, and also I wrote it ugly. 2s minus 2. So here, what happens at highest spins, so spins with matter spins higher than the actual gauge boson, is that the massless limit becomes bad. Here it goes bad on your nose. Here it's less obvious, but this this bracket, it goes in the denominator now for higher spins. For lower spins, it stays in the numerator, so everything's fine. But for higher spins, it becomes a pole, and this doesn't correspond to the normal physical poles in the channels like S1, 2, like ST and U. And so this is an issue that we're having at the moment. This bracket can be translated to like a square root of S1, 2, S1, 3 minus m to the 4th up to some phase. Yeah, it doesn't look like something that would come out of a propagator.
Do you know about the large Z behavior?
Yeah, that's a very relevant question. My derivation, in my derivation, I used the BCFW recursion where I added residues from 2 poles coming from propagators, but in principle, there's also the large Z, the infinity pole that could be there. So I just assumed that it wasn't there, otherwise I would have to add something. But since it comes from infinity, it's doesn't come from standard unitarity. I would have to add some more knowledge into the picture, which we lack. I don't know, I lack at the moment. This would not correspond to, this would correspond to adding some piece that is regular on the physical poles, because the physical poles, I want them to match my 3-point channels. So this piece can be in principle added, and actually people have studied if they can add something sensible here. Chung, Huang, Kim, and Lee in this paper but there's a lot of redundancy. It depends on your power counting. How many masses do you want to get? Do you allow to appear? Because when you add something that doesn't have poles in ST and U, you just to preserve your engineering mass dimension, you have to use some other mass dimensionful quantities, which are masses, right? So you end up adding more explicit masses to your expression. Well, in this expression, you just had them already. So all of this is despite the fact that my original shift 2 and 3, if I look at the final answer and I use it, nothing here shifts. So the only things that shift, if I look at the final answer, are the poles. So my answer is consistent with the with the vanishing boundary behavior. This is what is interesting about this answer as well.
It's automatic whenever you
No, it's not automatic.
yeah, if you neglect the boundary term, I think you assume.
No. I think I have done it. I have seen myself when I assume something, I compute the poles. I just compute the residues. Like we have tried shifts like that, and you get an answer, and it's first of all it's very ugly. It's much uglier than that, and then if you look at the large Z behavior, it blows up, even if you considered it to be good in your derivation. So sometimes it is used as a consistency check for things to be good, and things seem to be good from that point of view here, and here as well. So yeah, this is something interesting. Well, the other thing that another lesson from these answers is that well, first of all, I've been doing this for color dressed amplitudes. I'm sure that most of you have seen BCFW recursion used in the color ordered setting, but those are orthogonal operations. One is color, the other one is just using kinematic relations, kinematic shifts, and computing. So, of course, I am allowed to do that fully color dressed, which I did in front of you. And you could ask what happens to the color in the S23 channel. So my shift didn't see the S23 channel by itself, so S23 pole appeared out of the helicity factors. So this is something that often happens. From these guys, I got myself S23 in the answer. So so it's nice that the pole is there, but also a consistency check for this pole is that this pole should come from color flow like this. Which wasn't in this calculation because BCFW usually omits some of the poles and then reinstates them in a non-trivial way. But you can see that it's fine. On this pole, when S23 goes to 0, S12 minus m squared is equal to S1 minus S13 minus m squared. So these two terms combined with each other into a commutator because of the sign. So, wait, this is CD. So, just the form, the color dress form that I have, if you just, on the pole, it gives you the right color structure. So that's, I think it's a nice thing to notice in this setting. And maybe, yeah. I won't derive anything much anymore until the end, but I still want to, since they're on the board, I don't want to be writing them next time, so let me inspect more properties of these guys for a little bit. So actually, let's do color ordering to them. So both of these amplitudes look like T, TC, TD. Now let me just use labels here to be T2, T3, 1, 4 over S12 minus m squared S23 and T3, T2 S14 T13 minus S13 minus m squared S23 times some factor that depends on helicities, H2, H3, S, A, B, and everything else. But that factor is the same for everything else. It works just the same way for the all plus amplitude if you just shove in S23 inside. So just this form works for both of them, can be color ordered. Color ordering is something that is well defined in the adjoint representation. So far I've been really agnostic about the representation in which my matter particles were in. In the adjoint representation is when I take something like that and I just write I, A, J. So this becomes F1, 2, some internal index E. Let me call it K. I was calling it K before. 3, 4. And this color structure becomes 1, 3, K, F, K, 2, 4. Once I'm in the joint, I can I can expand them in fundamental traces, and that's something that is covered very well in Lance's lecture notes from way back. And I don't know a better reference for that, and I'm sure you have seen that. So these combinations of structure constants can be expanded into traces like this, plus reverse. And this gives me traces like 1, 3, 2, 4, minus trace 1, 1, 3, 4, 2, plus reverse. And now we can read off the coefficients in front of the traces, because the traces I gauge are linearly independent, so the coefficients must be gauge invariant. And so the color ordered functions will look like this. So trace 1, 2, 3, 4 appears here only. So it's just that part. Trace of 1, 3, 2, 4 appears here. So this is that part. And the other ordering is 1, 2, 4, 3. And it appears here. And it appears here in the reverse. The reverse contains minus trace, minus 2, 4, 3. Just reversing this trace. So I naturally get minus 1, 2, 3, 4, minus 1, 3, 2, 4. So this is the Kleist-Coif relation, or photon decoupling identity. And I can also rewrite it as f of S1, 1, 2 minus m squared, S1, 3 minus m squared. So you can read off the color ordered amplitudes right from there. But what I want to say here is that not only we get the Kleist-Coif relation, but we get a BCJ relation. 3, 4 equals 1, 3, 2, 4, S1, 3 minus m squared, S1, 2 minus m squared. You can just see that it works here automatically. So my gauge theory amplitudes that I constructed from the BCFW construction obey the BCJ relation. So Bern, Carrasco-Johansson, which are some of your supervisors, so you know very well. Actually, the massive case I had to do something with. Massive and flavored case, it just works the same. And coming back to Lance's question, with the massive, in the massive setting, there's a general statement at tree level that whenever you have BCJ relations, you get a consistent way to construct gravitational amplitudes through the double copy. And at tree level, the BCJ double copy is equivalent to KLT double copy. So all of that comes in a package once you have something like that working for you. Which brings me to my gravitational amplitudes that now I'm just allowed to construct through the standard just by using all of these statements that are well known in the literature. So, yeah, it's 2. Now this bracket now is squared, and I'm concentrating on the fully symmetrized double copy. I don't anti-symmetrize anything like before the break. S, S12, S23. So here I just used that equation that I think I had on the board. So actually I took this thing, and I took the other ordering, and I multiplied with S23, and I only did it with complete symmetrization. There was a spinning particle side here, and then there was some other spin here, but I fully symmetrized them, and what I got was spin S, which is just their sum. Total spin, I combined it in the maximal way. And the same works for the all plus case. And now the same issues that I mentioned for higher spins, now they start at spin bigger than 2. All right. So yeah, that's the end of my lecture. Please ask questions if you have them. Thanks. Oh, sorry.
Now that we have the amplitude, are we going to?
Yes. Yes. Next time. Yes. For which? Checked what? No. Oh, yeah. Okay. Yeah. No, I mean, I've done some stuff at higher points, but I'm not going to talk about that publicly, and there's nothing to be very proud of. Yeah, actually, something else that maybe I want to remark is that this calculation contains scalar QCD, contains massive QCD with Dirac fermions, massive quarks, and it also contains the QED with electrons, and because this ordering here, it only has poles 1, 2, and 1, 3. So actually, this corresponds to the QED amplitude. If you just replace the coupling constant by square root of 2e. And this QED works for the massive electron, but also I have the spin 1 case in my picture, so it also contains an amplitude for photons deflecting a massive W boson. So all of them are embedded into this derivation. You can just read them off. And the derivation is surely correct for them because those are lower spins for which the boundary behavior that was the issue, the unknown bit of the derivation, for them, we know for sure that everything at large Z works well. So it's standard model calculation as at the same time as something relevant for black holes in the next lecture. Yes?
So I guess this funny factor that appears in the denominator, I don't think it ever blows up in the S12 channel or the S13 channel. Because S12 would be positive and S13 negative, and then it would be 0.
You mean in the O plus case? Oh, no. Oh, you.
Plus minus factor, the 312.
Oh, 3, 1, 2. Yes. OK. So you were
But I
saying?
do think it can blow up in the S23 channel, where 2 gluons come in and make 2 massive particles. Because if the scattering angle is 0, then momentum 1 can be written as a linear combination of the 2 incoming gluons. But maybe it works in the configuration you need for black holes.
Yeah.
Which is the S12 channel. Maybe you're far enough away from the singularity that it's okay when you go into classical.
Yeah. Well, apparently for lower spins it works. Yeah. We do want that.
Black holes.
Yeah. We do want high orders in spin as well. Yeah. So let's leave that for tomorrow. Thanks again.